Hello there, Mr. Sutton here with the BC Calculus 7-7 Part 2 homework solutions on geometric, nth term, and ratio tests. On this one, we're trying to figure out the convergence or divergence of this series. So we start with the nth term test. Looking at my two terms here, limit as n approaches infinity, we have a bottom-heavy function. Exponential growth is going to outstrip, well, this is at best polynomial growth, if not worse. So this goes to 0. And we can't just say this diverges based off the nth term test. So we're going to try the ratio test next. So let me take the ratio of the n plus 1 over nth term. So limit as n approaches infinity, absolute value of, and now in the top we're going to have n plus 1, ln of n plus 1 over 2 to the n plus 1. So that's all in one big fraction up there in the numerator of this ratio. In the denominator, we just have this term, the nth term. And now doing a little same change flip to simplify this fraction. In my numerator, I've got 2 to the n times all of this other stuff, n plus 1, ln of n plus 1. Denominator, I've got the 2 to the n plus 1 and this n ln of n. Let's go ahead and simplify this as much as we can before we try approaching infinity here. So I've got these two exponential terms. Dividing my bases, I can subtract the exponents to get just a 2 to the 1 in the denominator. And then what do we do next? Well, as n approaches infinity, these plus 1s are going to go away. We can ignore those slower growing terms. So we've got something equivalent to n ln of n in the numerator. And now we can just reduce this directly. This is just going to be 1 over 2, which significantly is less than 1. So by the ratio test, this is going to converge. On this problem, we're trying to check the convergence of this series. So we always start with the nth term test. Limit of this whole thing as n approaches infinity is going to be what? Well, n factorial grows faster than exponential growth. So this is going to be a top-heavy function. So we're going to be approaching some kind of infinity. Because we have this alternating -1 to an exponent, it's actually going to be a plus or minus infinity, but it doesn't really matter. The key point here is that this does not equal 0. So therefore, this is going to diverge by the nth term test. To see if this series converges or diverges, we first consider the nth term test. So taking the limit as n approaches infinity of n factorial over 2 plus 1 factorial, is this top or bottom heavy or neither? Well, think about it this way. 2n plus 1 factorial is n factorial times a bunch of other stuff. So if n is growing, then this term is going to keep getting bigger and bigger after you cancel out all those factorials, or at least the denominator keeps growing. So this is going to be a bottom-heavy function and go to 0 if you do take that limit as n approaches infinity. That's inconclusive, so we're going to need to use another test to figure out if it converges. Let's use the ratio test. It's not geometric, so ratio test is all we kind of have at this point. So I'm going to take the limit of the absolute value of the n plus 1th term over the nth term. So what that looks like, we're going to have n plus 1 factorial up here, and this is going to be 2 parentheses n plus 1 factorial in the denominator. So a whole bunch of parentheses and n plus 1s. Down here in the big part of the denominator, the big denominator I should say, we have just the nth term. All right, same change flip. Let's see if we can reduce all this. So in the numerator, I have n plus 1 factorial and 2n plus 1 factorial. In the denominator, this is going to be, let's see here, 2n plus 2 plus another one. It's 2n plus 3 factorial. And this n factorial is also down there. And let me reduce this as much as I can. N plus 1 factorial and n factorial mostly cancels out except for an n plus 1 up here. And 2n plus 1 factorial and 2n plus 3 factorial, that's going to leave a 2n plus 3 and a 2n plus 2 in the denominator. So I've canceled out all my factorials. There's just a few of those leading terms left over. This is all going to be essentially an n over 4n squared situation. This is bottom heavy, so this is going to go to 0. Since that's less than 1, that means this series is going to converge by the ratio test. For this problem, we're trying to check the convergence of this series. Just applying my nth term test real quick in my head here. n factorial grows way faster than n plus 1, so this will go to 0 if I take the limit of the nth term. So that's not going to prove anything. I need to use the ratio test next. It's not a geometric series, so let me use the ratio test to get to the bottom of this. So I have the n plus 1th term. That would be n plus 1 or n plus 2 over n plus 1 factorial. So that's going to go in the numerator of my big fraction here. So I have the limit as n approaches infinity, absolute value of n plus 1th term over the nth term, which was already kind of given to me. Same change flip. I've got n factorial and n plus 2 together in the numerator. Denominator, I've got an n plus 1 and an n plus 1 factorial. And now reducing this a little bit, n factorial, n plus 1 factorial, that's really just n factorial times n plus 1. So n factorials can cancel. That leaves me with just an n plus 1 and an n plus 1 in the denominator, or I could write n plus 1 squared if I wanted to. And now, reducing all of this, I've essentially got, if I ignore the slower growing terms, I have an n over an n squared, which is just going to be 0 because we have a faster growing term here. Now, the important piece is that 0 is less than 1, so that means this is going to converge by the ratio test. On this problem, I want to know which series converges for all real numbers x. So it's kind of hard to prove convergence for all real numbers, but what we can do pretty quickly is prove that 4 out of 5 of these diverge for certain x values. Because if we prove one case where any of these diverges, we don't have to keep looking at that answer choice. So what's going to make these diverge? Well, to make things diverge in general when I have fractions, I want to make the numerators grow as fast as possible. And I notice that all of these numerators have x to the n's in them. An exponential function like x to the n is going to shrink if x is less than 1, and it's going to grow if x is greater than 1. If x is greater than 1, which of these is going to grow without bound? Well, in choice A, so this is my if x absolute value is greater than 1 reasoning, then in choice A, we have an exponential over linear, so this is going to diverge because its nth term test makes this go to infinity. Choice B, it's a top-heavy function, so it'll also diverge. Same thing with choice C. With choice D, we have n factorial, which kind of beats everything. So choice D, it doesn't look like is going to fail the nth term test. Choice E, again, n factorial beats almost everything, so E is going to diverge. So A, B, C, and E are all going to have faster growing numerator terms and diverge by the nth term test, which allows us to pick answer choice D if we wanted to. Now, if we don't really believe answer choice D, we can prove that this converges for all x's using the ratio test. So let's go ahead and do that. I'm going to take the limit as n approaches infinity of absolute value of n plus 1th term over nth term. So my nth term, n plus 1th term, that's going to be e to the n plus 1, x to the n plus 1 over n plus 1 factorial. And I'm going to divide that now by the nth term, which is essentially all of this stuff. Same change flip. I've got e to the n plus 1, x to the n plus 1 times n factorial in my numerator. Denominator, I've got n plus 1 factorial and e to the n, x to the n. Doing a little reducing. In my numerator, after I reduce these exponents by subtracting the n's from the n plus 1s, I have e and x. In the denominator, I can cancel out an n factorial with the first n factorials of this n plus 1 factorial. That leaves me with just an n plus 1. And now, as n approaches infinity, the only variable here is n. E and even x are being treated as constants in this setup. Only n is growing. So we have two constants over something that's growing. This is a bottom-heavy function, which means the limit as n approaches infinity on this is 0. Since that's less than 1, that means that this is going to converge for all x by the ratio test, which again allows us to pick answer choice D. On this problem, we're given this e to the n over n factorial series, and they're just coming out and telling us if the ratio test is applied, which results implying that our series converges. Well, ratio test makes sense here, because if you do the nth term test, this is a bottom-heavy function which will go to 0 and be inconclusive. So using our ratio test then, we need the limit as n approaches infinity of, and now we have a big old fraction inside absolute value. On the top, we're going to have the n plus 1th term, so e to the n plus 1 over n plus 1 factorial. In the denominator down here, we just have the plain nth term. At this point, we're reducing the fraction and simplifying. So same change flip. I've got e to the n plus 1 and n factorial in the new numerator here. Denominator is going to have the other things, n plus 1 factorial and e to the n. I can reduce these exponential terms by subtracting the exponents. So this is just e to the first power in the numerator. Now the n factorial and the n plus 1 factorial, so this n factorial cancels out the first n factorial factors of the n plus 1, leaving just the n plus 1 at the very beginning of that chain of multiplication. And now we just have to take the limit as n approaches infinity of this. Well, we have a constant over something that's growing, so that's going to go to 0. Since that is less than 1, we would say this converges by the ratio test. Now we actually had to find the inequality that we used to get this. So we have a limit as n approaches infinity of e over n plus 1 less than 1. Let's see if we can find that here. So it's not a or b. C, we have n plus 1 over e, that's upside down. D, e over n plus 1 less than 1. That looks good. And then e had a factorial that we didn't want, so yeah, choice D. On this problem, they want the value of this infinite series. Typically, when they ask for the value of an infinite series, it's a geometric or some other special one. This is geometric. We have repeated multiplication going on here. Since it's geometric, I just need to know the first term in the common ratio. So a1, my first term, that's what I get when I plug 0 in for n. That'll just be 1. For the common ratio, that's what I'm multiplying by over and over again. That's the base of this exponential term here, so negative 2/3. We have an option for the series diverging, so I better check to see if this converges or not. To do that, let me take the absolute value of the common ratio and compare that to 1. So absolute value of r is going to be 2/3. That is less than 1, which means this does converge by the geometric series test. Let me go ahead and write my infinite sum formula now, a1 over 1 minus r. So this is going to be 1 over 1 plus 2/3 minus negative 2/3. This is really 1 over 5/3, which is just going to be 3/5. So choice C. On this problem, we want the value of this series. In general, when they want the value of an infinite series, it means they're thinking you can actually take the sum of it, which means it's probably geometric, or else it's one of those weird Maclaurin series that you have to recognize which function it is and convert it into function form. But that's really essentially what you're doing with the geometric series anyway when you use the infinite sum formula. So this actually is geometric. We can see that if we rewrite it a little bit. This negative 3, I can rewrite as negative 3 times negative 3 to the n. So basically, I'm just getting it so I have two exponents that have n's, so I can move their bases in together inside a big fraction. So this is now going to be negative 3 times negative 3/5 to the n power. And now I see this is clearly a geometric function. What's our a1 value going to be? Well, if I plug 1 in for n, this is going to be negative 3 times negative 3/5. So that's going to be 9/5. And then for my r value, that's the thing that keeps getting multiplied by over and over. That's this negative 3/5. And before I go ahead and actually whip out my infinite sum formula, let me make sure this thing converges at all. I mean, it probably does because none of the answer choices say diverges. But just to be on the safe side, the absolute value of my common ratio is 3/5. That is less than 1, which means by the geometric series test, this is going to converge. So let's go ahead now and converge it. Using my infinite sum formula, a1 over 1 minus r, I can write 9/5 over 1, this will be plus 3/5. So this is 9/5 over 8/5 if I do 5 plus 3 over 5. And I could either do same change flip, or I just realized that I've got the same denominator, so I can cancel those. This ends up coming out to 9/8, which is going to be choice D.